things to remember. You have a position versus time graph here. It tells you where the object is at various points in time. With that, you can figure out what kind of motion is going on, okay? And you can use formulas that involve position, time, and possibly velocity and speed, okay? Those are the things you can get from this graph. All right, so if we're looking at formulas that might come into play, okay, that are on our formula sheet, this one, okay, displacement is final position minus initial position, okay, velocity is displacement divided by time, speed is distance divided by time. That's really about the only formulas that are going to come into play for a position versus time graph, because that's all I can get from this graph. All right, I'm going to give you a few minutes here, okay, work on that one, and then we'll go through it again. All right, so the first thing they want us to find is the total displacement, okay, so that's going to involve that formula there. That calculates total displacement, and it uses positions. I have positions because I have a position versus time graph, okay? So I've got to find my final position. Final position is where I am at the end. Well, that's right here. So I just come back across, and that final position is 0.5. Right, so 0.5 is my final position, okay, minus my initial position. That's what the formula says to do. Well, my initial position, that's at time 0, is positive 0.2. So, right, so 0.5 minus 0.2 is positive 0.3 meters per second. Is the positive important? It is. It's displacement. You don't put the positive on, it's the distance. Okay? All right, speaking of distance, the next part of this is to calculate the total distance traveled. That still, oddly enough, uses the displacement formula, but it breaks it down section by section because I need to know how far this thing goes in total. Right? So how far do we go here? 0. Yeah, it doesn't change position. Then we go from 0.2 to 1. Right? So that's 0.8 meters. Then we stick around at 1.0 meters for a while, and then we go from 1 meter back down to 0.5 meters. So that's another 0.5 meters. Since our distance doesn't care whether I went forward or backward, I simply add those two numbers together to get a total, don't need that, total distance of 1.3 meters. No vector. Yes. Okay, average velocity, average speed. I've already done all the legwork for those by finding the displacement and the distance. I just need to do the calculations involving now these two formulas here. Okay, so to find the average velocity, okay, so average velocity is going to be the total displacement divided by the total time. I calculated the total displacement to be 0.3 meters. I'm dividing that by the total time, 7 seconds. Okay, and when I do that, I should get positive 0.04 meters per second. All right, everybody okay with that? Questions there? Okay. And then for the average speed, okay, average speed is distance divided by time. As we said, I already did the legwork. I calculated the distance. It's 1.3 meters. That took the same amount of time, 7 seconds. So when I do that, I should get 0.19 meters per second as my average speed. Okay, that is actually a pretty typical exam question. Okay, there are 4 things that I can ask you to do with an irregular position versus time graph. Okay, obviously a regular one would be like the ones in our lab where it's just a straight line. Okay, then we can use y equals mx plus b. I can't use y equals mx plus b for this one because it's all over the place. Okay, there is no single line. Okay, everybody okay with that one? How that one worked? Okay. Let's try this one, okay? Another position versus time graph, asking us for similar things here, okay? But it is breaking the graph up a little bit. So distance traveled between 0 and 90 seconds, displacement from 20 seconds to 80 seconds, average speed over the whole trip, average velocity over the whole trip. So similar, okay, to the last one. for this one here, okay? First part, distance traveled between 0 and 90 seconds. So that's just how far we go, okay? Doesn't matter which direction. So at the beginning, we're at a position of 0, and then by the time we get to about 40 seconds or so, okay, we're at 400 meters. So that's 400 meters, okay? Then to 90 seconds, which is about here, okay, we go from 400 back to 200. Okay, so that's another 200 meters, right? That means if I add those together, I get a total distance of 600 meters. Everybody okay with that? Okay. Your graph's got a few more things on the x-axis than mine does, right? The displacement from 20 seconds to 80 seconds. All right, we have to remember then that displacement is final position minus initial position. Okay, my final position at time 80 seconds, okay, would be about here at 300 meters, okay, and I'm starting at 20 seconds, which would be probably right about here, okay, at 200 meters, right? So 300 back to 200 is, okay, so sorry, I'm going to do this. 300 meters, okay, minus 200 meters gives me 100 meters in a positive direction, okay, for that one. Everyone okay with that? Sorry, my graph really needs more lines on it. Average speed over the whole trip. Okay, average speed is total distance divided by total time. Okay, now here's a critical graphical analysis skill that saves me time. In the first part, I went from 0 to 400. And then over the rest of the trip, I got back to 0. Would you agree? Okay, and I basically came straight back to 0. So if I went forward 400 and backward 400, how far did I go? No, how far did I go? 800. Okay, I don't have to really like put in all the final position minus initial position stuff. I can look at that graph and go forward, backward to where I started. Okay, 400 up, 400 back. Okay, and just say this is 800 divided by 100 seconds. That gives me 8 meters per second for a speed. Okay, it saves me doing a bit of math. All right, and then average velocity over the whole trip. Well, that one's going to be pretty easy because, as I said before, critical analysis of this graph says I started at 0 and I ended at 0. I didn't go anywhere. What's my average velocity? 0. I don't even have to plug anything into this formula. I can recognize that by looking at the graph and save myself work. Okay? That's what we're trying to build to, guys, is being able to look at a graph and go, yep, done. Okay? Without having to do a heck of a lot. Right? That's why I can put graphs like this in a multiple choice question. Right? Like I could put that in there and say, what's the average velocity over the whole trip? That's a multiple choice question. It doesn't even require you to really do much work, does it? It just requires you to recognize something off of that graph. Okay. All right, any questions on number 2? Okay. All right, this will be our last position time graph. Then we're going to look at velocity versus time graphs. Okay, so give this one a try here. Okay, it's kind of an exam level question too. It's not terribly involved. Okay, so give that one a try, and then we'll go over it in a few minutes. Okay, so another position versus time graph. Okay, we want the displacement from 0 to 4 seconds. All right, well, we already know that displacement is final position minus initial position. Okay, so our final position is -4. Well, that was very straight. Okay, -4 meters. Okay, and we're subtracting the initial position, which was 0. So our total displacement during that time is -4 meters. Okay, that was pretty easy. All right. For part B, total distance traveled. All right, well, that's going to go section by section again. So in this one here, I go from 0 to -4. That's 4 meters. Then I don't go anywhere for the next 2 seconds. And then I go from -4 to +6. That's 10 meters. All right, so the total distance traveled is 14 meters. Everybody okay with that? Okay, did I use final position minus initial position a couple of times? Yes, okay, but then I just put it together for distance. Okay, average speed over the whole trip. Average speed is total distance divided by total time. Well, I just did all the work for that. Okay, I know the total distance is 14 meters. Okay, I know the total time is 6 seconds. Okay, and when I divide those, I'm going to get 2.3, meters per second. Questions on that one? Okay, then average velocity over the whole trip. Okay, so average velocity is displacement divided by time. So final position minus initial position divided by time. Okay, our final position is 6. Our initial position is 0. Okay, total time, 6 seconds. 6 divided by 6, positive 1. Woo, positive 1 meters per second. Okay, everybody all right with that? Okay, let's look at a velocity versus time graph. Okay. Yesterday, when we were working on velocity versus time graphs, okay, we said that if you want to get the displacement, you have to use average velocity times time. So on a velocity versus time graph, the formulas that are available to you are ones that contain acceleration, velocity, time, okay, as well as these. Okay, and v equals d over t, the other one, the scalar version. Okay, those are available to you. Okay, but we have to remember that they are average speed and average velocity, and that means total displacement and total time. So if we're looking for displacement, I want to use average velocity times time. We found out that that basically means you have to break this graph up into a bunch of what? Yeah, well, somebody said it. Different shapes. Okay. Now, if you're breaking it up and you're making a triangle, do know that that triangle does need to be a right angle triangle. Okay. So because you got a couple here where you can go like, oh, I'll just make that one big triangle. No, got to be a right angle triangle. Okay. When you make these. All right. Okay. I'm going to leave you to that for a little bit. Okay. See how you do with it. In a few minutes, we'll go through part A. And I'll draw in the shapes for part B, but I want you guys to try and get those first, okay, before you see me do them. All right, so velocity versus time graph, we do things a little differently. Okay, we can use this formula now because the graph is showing us velocity and time. Okay. All right, so for part A, I'm just using this formula here, right? Don't have to manipulate it. I'm trying to solve for A between 12 seconds and 14 seconds. All right, so here's 14 seconds. Here's 12 seconds. Okay, so 14 seconds is my final velocity. So if I'm plugging in here, okay, I'll have A equals my final velocity, which was -6, minus my initial velocity, which is +2. Okay, and between 12 and 14 seconds is 2 seconds. Okay, -6 minus 2 is -8. Divided by 2 gives me -4 meters per second squared. Okay, everybody all right with that? We just have to read the numbers off the graph, plug them into the formula. Sometimes it's that easy. Okay. Now, the next part isn't hard, it's tedious. Because you're going to do the same thing basically a whole bunch of times. But it does require you to identify when a certain type of motion starts and ends. Okay, so how many people think they have the shapes drawn? How many people are still in the process and would like a little bit more time to do the shapes? Okay, I'm going to give you about 2 more minutes to draw the shapes. Not to worry about calculating the answers, just to get the shapes all drawn. And then I'll draw them up here and you can compare to what you did. So again, this is going to require a little bit of those critical graphical analysis skills. Okay, so between 0 and 2 seconds, do I have a shape to draw? Why not?
It's on the x-axis.
Right, it's on the x-axis, which on a velocity versus time graph means the object's not what? It's not moving. Its velocity is 0. It's going to have no displacement. Its average velocity is 0, doesn't go anywhere. Okay, then after 2 seconds and until 5 seconds, the object accelerates negatively from a velocity of 0 to a velocity of -3 meters per second. Okay, so that is the end of one of motion. Okay? It accelerated at a certain rate during that period of time. Then it turns around and it starts to accelerate in the other direction. Okay? So that represents a different part or motion in this whole trip here. Okay? So that's going to be its own little triangle as well. Okay? Then you can see that the angle changes. If the angle, or what's the other word for that on a graph, starts with S? The slope changes. That means the acceleration has changed, and that marks a new section of the graph. So there is this part of the graph here where it's accelerating in a positive direction, but at a slightly different rate. Okay? Then there's a section of the graph here where the object travels at a constant velocity. Well, that makes a rectangle. Those are easy. Okay? And then there's a section of the graph where it turns around and accelerates backwards, okay, for about a second and a half. And then it really accelerates in a negative direction, okay, for, this looks like about a half a second here. Does that match your graph? This looks different on my graph than your graph, doesn't it?
There's not like this different slope of the line.
Right, this should have been over to like 15 seconds or something, right?
Yeah.
Okay, I blew it when I made that one. I'll have to double check that one. Let me have a look here. We'll just do this so that I have the right one. Sorry, guys. Thought it looked exactly the same, but apparently it doesn't. Oh, that's ugly. Okay, but it'll have to do. Okay, so this one will match yours then. Okay, so we'll have these two triangles which we already identified, this triangle which we already identified, this one here that was a half a second, this one here that was supposed to be a second and a half that I messed up. Okay, then there's this one here, then there's a rectangle, and then there's a little triangle at the end. Okay, 9 shapes I believe. Okay, because there's 9 different types of motion on this graph, 9 different accelerations or constant velocities that this object undergoes. Okay, how are we doing with the shapes? Okay, was everybody pretty close? All right, what do you have to do now? What do you have to find for each one of those shapes? Their area. Okay, so got to get on that, find the area of those shapes. We'll talk about the areas of those shapes in about 3 or 4 minutes. Okay, so on these ones here, we got to calculate all the areas. So this first triangle here is 3 seconds on the base and -3 seconds for a height. Okay, so -3 times 3 is -9, but it's a triangle divided by 2, and you've got -4.5 meters in that box there. This box here has a base of 1 and a height of -3, so -3 times 1 is -3 divided by 2 because it's a triangle. Okay, and you've got -1.5 meters for that triangle. Okay, then we've got this little triangle here that's 1 on the base and 2 high, so 1 times 2 is 2, divided by 2, you got a 1 meter triangle there. And then this rectangle goes on for 1, 2, 3, 4, 5 seconds, 5 times, so 5 on the base, 2 on the height. That's +10 meters, this is +1 meter. Okay, and then this one here is really skinny. It's only a half a second on the base and 2 high. 0.5 times 2 is 1, divided by 2 is 0.5. So that little box there is +0.5 meters. This very tall triangle here has a base of 1.5 and a height of -6. -6 times 1.5 is -9. Divide that by 2, and you've got a triangle with an area of -4.5 meters again. Okay, and then this triangle here only has a height from -2 to -6. So its height is -4, okay, and its base is 2 seconds. -4 times 2 is -8. Divide by 2, you got -4 meters. Okay, and then you got your rectangle here that's 1, 2, 3, 4 on the base and -2 high. So that's -8 meters. And then we've got this little tiny triangle here that's 1 second on the base, -2 high. -2 times 1 is -2. Divide by 2 because it's a triangle. We got -1 meter. And then for along the x-axis for the last second, nothing to draw there. Okay, everyone all right with that? Okay, I know I went kind of fast, but I don't want to run out of time here. Okay, so what do I do with all those numbers to get the total displacement? Add them all together with the negatives. Okay, I'm finding displacement, which is a vector quantity. So when I do that, luckily I still have that number right here. Okay, so went -1.5, -4.5, 1, 10.5, -4.5, -4, okay, -8, and -1. Added them all together, I got a total displacement of -12 meters. Okay, which is exactly what I should get. -12 meters when I add all that together. Now, here's a quick critical graphical analysis skill that can help me decide whether that number makes sense or not. Does this object end up in the negative part of the graph more than the positive part? Okay, then it sort of makes sense that I should get a negative number. I'm good with that. Okay, next thing, average velocity over the whole trip. I just did all the work for that, really. I've got -12, and that takes 20 seconds. Okay, so V equals d over t. This is, of course, velocity and displacement. -12 over 20 is -0.6 meters per second. Okay, so we did all the hard work already for that. All right, D, the average acceleration between 14 and 20 seconds. All right, so acceleration is final velocity. That'll be 0 minus -6, and that takes 6 seconds. Okay, 0 minus -6 is +6. 6 divided by 6 is +1 meters per second squared. Everybody good there? Okay, don't pack up. Don't pack up. All right, average speed to 20 seconds. All right, so that means I take all of these numbers. To get the total distance, what do I do with all those numbers again? Add them up, but without the negatives. So in my calculator, what I did is I just put in the entry and then deleted all the negatives, and I got a distance of 35 meters. Okay, then I take 35, divide it by 20, because speed equals distance over time. Okay, that's supposed to be down here. Okay, and I get 1.75 meters per second. All right, everybody okay with that? Okay, now very quickly, if I give you a graph like this, okay, honestly, for part A, I would not expect anything. This would be a multiple choice question. Why? For part A, I have a velocity versus time graph, and I'm supposed to calculate total displacement. Can I do that without calculating and just looking at the graph and being critical? I can. If I look at this graph critically, I see that what happens below the x-axis and what happens above the x-axis they're identical. It's like a mirror image. Well, that means then that the area of this and the area of that are the same. One's negative, one's positive. This thing didn't go anywhere. Okay? I can do that without having to do any calculating. It's one of those critical graphical analysis questions. I would totally make that a multiple choice question. Okay? Now, second part of that, average acceleration, pretty simple calculation there. Okay? That's just going to be one of these, VF minus VI over T things. Okay? -8 and +8. So 8 minus -8, and that takes 10 seconds. That's going to be +1.6 meters per second. Okay, I would totally do that as a multiple choice question as well, because it required basically nothing of you. All right, average speed over the whole trip. Okay, well, I got to do two simple things there. This box and that triangle. 8 times 5 is 40. Okay, 8 times 5 over 2 is 20. Those two are exactly the same. 60 plus 60 is 120. Okay, divide that by the 20 seconds. Okay, and you've got 6 meters per second. See, like that graph, that's a great exam level graph. because it doesn't require you to do all the tedious crap you had to do in the graph before. But it's the same skills, okay? And it's the same, I look at this and I can identify things without having to do all the tedious work, okay? That's what we're trying to move towards. All right, questions on any of that for today? Okay, I know I made you work hard today. Good job.